Hey, hello guys. Today we are going to do numbers and names number 7. And this is mostly about something which is called definitions. Do you know what definition is?
Yes.
It's something like you tell what is it and what it is not, right? So you heard a lot of definitions. In mathematics, definition is very important. Not only mathematics, in physics too. But what we're going to see today, the definition is a very tricky thing actually. You should really think about it when you do these definitions, when you read about definitions and all about it, right? So what definition is in general? We may say that, like, we try to define something which we call this thing, like this tree, this square, this thought, whatever. Something that we call this, right? This. So this is something like this. So what is this thing? This is a border which separates the thing that we call this thing from something else. So something outside of this border, it's all, how can we call this? Everything outside. If this is... Huh?
I have a question.
Yeah, okay, good question.
What is outside the border?
Hmm?
What is outside the border?
Yeah, nothing, not this.
Oh.
Something that is here, right? We separated something that we call this, like some tree maybe, or some person, like Peter or Boris or whatever, or Ilya or Katya, or maybe our planet, right? Something particular. And we want to define it, right? So we're talking about this which we want to define. We want to find out what's the definition of this, right? So this is this. It's selected from everything else. So how could we call this everything else? What do you think? The best name for this?
Everything else?
Yeah. Except this.
This and
Something else.
Yeah, okay.
well, right, but this.
No,
what's
this
the
is
opposite?
all this is here. All this is here. So everything else is out there. So how we call this all out there?
So this is a cup, and this is. Is this a cup?
No.
This is something. This is something.
The opposite of this.
Which is
Like for example, a tree, right? Maybe
Something.
tree.
Oh,
sit.
yeah. Not
Yeah.
this.
Not this. Yeah. This is this, and this is not this. Everything else, not this, right? So the shortest name for this should be not this, right? And this border separates this from not this. If we go from this in any place, right, and cross the border, this becomes not this. It becomes just, we go from this to not this, right? So not this is everywhere here, everywhere. And this is called negation. Adding not is called negation in logic. Or I don't know, the common term may be denial. So you just remove this and everything except this is not this. So if here is a tree, here is everything else but not a tree. Particular tree, like a fir tree, right? So there are other trees, whatever other trees, but not fir trees. Any plants, any grass, any animals, anything, but not this, right? So let's take a look at this border. What does it do? When you pass this border in any direction, right? Here, here, or here, or here, right? What happens? This transforms into not this.
Yeah.
So it looks like that this border actually is what is called not. Do you understand this? Yes. So this is a not border. Not here. Not everywhere is not. Right. This is first thing. The second thing with this border is another interesting thing. If you think a little about it, not now but maybe later, just a little think about this thing. Let's find out something here, right? Somewhere in this area of not this, right? Oops. Something here. So this is all not this, and this is part of all of this, not this, right? Maybe this is all animals, and here like all plants, but not this fir tree, right? Like for example. And you think about it, how can it be really be somewhere here? What do you think? Here is this, right? This is the border, and here is something not this.
You could have another bubble.
Can it be here, or
Yeah.
or it should be, or we should display, should draw it somewhere else? What do you think? Is everything okay with this position?
Except in this thing, because it's all the plants, not just this.
Okay, but I'm talking about this picture. So here's the border, right?
Yeah.
Which adds not to this, right?
Yeah.
And here we have this. So we have something else in between. Is it okay?
Yeah.
But we already have not here. And what this may add? This may add something else if you move here, right, from here to here. So what I mean actually, maybe I'm maybe a little confused. I'm making you a little confused. But what I mean here, that actually you may put this thing, whatever it is, right at the border, because exactly when you come past the border, you go into anything which is not this. Not this is everywhere here, right at the border, not somewhere else. You may picture it like this, like the whole field of everything, right? But actually this is very interesting thing, because it is because it's bordering with not this. It's bordering it with any which is not on this border. If we picture this, this border is very impressive thing. It touches each thing which is not this, each one, because this border is border not this, not fur, not animal, not planet, not star, not this, not this, not this. Everything what we see here, actually it is on the border. In another way, we can say that the border of this is the whole thing which is not this. So this is the border, is everything this. This is all the border. Just think about it. I'm not sure that it's like right away it's understandable, but just think about it. It's a very interesting point. That actually when you pass the border, actually this is it. You can pass to anything which is not this. So the border is very interesting thing. If you picture something somewhere here, actually it's not here, actually it is on the border too. Everything is on the border. So that's just to understand that it's not that simple as it seems maybe in the beginning. But anyway, if you think about not this, right? So we think that this and not this are the opposite things, right? So if we want the definition for this, we may say not this. So come here and back. So if we talk about in abstract, it's maybe a little sounds a little abstract, but if you say what is this, like what is a dog, you and they start explaining. You say, okay, dog is something not cat, not the grass, not this, not this, not this. So by naming all which is not this, you're actually defining the cat, because you're removing everything which is not cat. Understand, right? It's understood.
Yeah. That makes
So
sense.
actually, one of the way to define something, it is to define which is not that. So cat, not cat. Fir tree,
Yeah.
not fir tree. Okay. So, and if when we understand this, we understand the interesting thing that actually, what actually not is. Not is exactly the border,
That's
right?
so weird.
So we may say that definition is a border.
Oh yeah, you described it, but nothing else.
Mm-hmm. 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 So it is definition. Each definition is some kind of a border. And why we need this? Because if you this kind of understanding. Because when you remember, if you remember, I once told you that the border is any border is a very interesting thing. It is at the same time like left or right. Oh, okay. Jesus. Left or right, right? And the border between it, right? When you come to the border belongs to right and left at the same time. So border separates like left from right, but at the same time it unites them or connects them, right? It's a bridge. It's always a bridge between left and right. And this is a feature of any border, whatever, like a river, like border, like two states are separated by the river. Yes, they're separated, but they are connected too with this river, right? If you okay, we talk about the door, right? The door is one of the most famous examples of that kind of border, right? But even a wall, it's not only separates the rooms, but actually it's a connection of certain way. You can hear through the wall, you can knock through the wall. So it is sort of connection. Even if you want, you can break the wall and come through, right? Because it is the border, still the border.
Temporary border.
Yeah, temporary, yeah, sort of. So any border is trans,
Right.
how you say, I don't know. Or can be overcome, right? Each border can be overcome. Okay?
Can be transgressed.
Transgressed, yeah, okay, transgressed. And another feature of this transgression, right? Remember, we talk this and not this are opposites, right? Not is the opposite. Negation is the opposite. So what is preserved when you go from this to not this? It's easy question, should be to you now.
So you go from this to not this?
Yes, if you go from this to not this, it's sort of a what is called this transformation. This transformed into not this. Okay, we go and see this and this. Suddenly it happens that not this to become not this.
Yeah.
We go forest and then forest ended, right? The field started, right? It's not a forest, right? So we passed the border.
This as Canada, and then all of a sudden you go for so long that you end up in the U.S.
Yeah, right. Exactly.
It'll take forever, but it's
Or
possible.
like valley and then mountains, right? Mountains, valley, whatever, right? Sea, the coastline, right? Coastline is the border between sea and the continent, right? Or the island. So what is this? If you remember the previous lesson, what this transformation means? This to not this. Okay, 1
Transition,
to
right?
minus 1. Transition is symmetry. Remember? It's a symmetry.
1 minus to minus 1. What the?
If
That is, yeah. This is
you transform 1 to minus 1, so just add minus, negation, negate 1, right? 1 to minus 1. What is preserved in 1 when 1 is transformed to minus 1?
1.
Huh?
1.
1, right. Here is 1. 1 is preserved. And what is preserved here when you something, what you call this?
This.
This, exactly. So this is here and here, but here it is like with the sign plus and here's the sign minus, right? Something like this. So we have this in mind. When we think about not this, we're having in mind this. When we think about this, we're having in mind this. So this is preserved in this thing. And this is one of the kind of the symmetry, actually. The border symmetry. And this is very important. If you understand the whole thing here, I want you to think about these things because it is very important to understand. Now what we'll go a little further. Remember we talked about axioms, right? Or the other word for axioms are laws, right? So axioms in mathematics, laws in physics and society, right? Some other things too, but we won't touch it right now. Okay, so remember axioms of geometry, right? What was okay, maybe okay, no, later. Okay, axioms of geometry. Remember there were like points and straight lines, right? So one of the axioms means that says one of the Euclidean geometry, Euclid, one of the axioms means that if you have 2 points, separate points, right? There's only one line can be passed through, straight line. Only one straight line can be passed through these 2 points, right? The other, like for example, the other pretty famous axiom means that if you have a line, right, and you draw a parallel line, there is a definition for this, but we won't touch it. You understand what parallel means, right?
Yeah.
So these parallel lines will never intersect.
Yeah.
Or maybe they intersect in the infinity, but they never intersect here. And some other axioms, right, which says this and this and this and this and this and this. But let's take a look at this axiom. What it actually says. It says, like the first axiom says, that if you have 2 points, right, you can draw only one straight line, right? What it says, that if you have something which we call geometry maybe 2, geometry, like Euclid geometry number 1, right? Or version 1. Geometry version 2. That we can say that something opposite to this. We say, okay, we have 2 points, but there are any number of straight lines can be drawn through these points. Any number. Opposite. What we did here. If you think a little, what we did, we say not this, not one line, right, but whatever lines. Not one, but, right? The same thing like for the second axiom. We can say, okay, in Euclidean geometry version 1, the parallel line does not intersect with the parallel lines do not have a common point, do not intersect each other, right? But maybe in geometry number like 3, version 3, right? There is intersection. And maybe many intersections. We just say, no, our axiom is not just say, not correct, right? That's all. We have something opposite. So parallel lines can intersect. Here they cannot intersect. We say no, they can intersect. So what we did in the first time and the second time, we actually, if you look, we negate the axiom, right?
Huh?
So in a certain way, when we negate, we actually define. So we say something geometry version 2 negate this geometry, but this means that there is geometry version 1 too, which has this point. So we have different definitions for different things actually, because these straight lines and points may actually be interpreted very different in other geometries. But even without it, definitely we will have different types of geometries, version 1, version 2, and version 3, whatever. There are many axioms. You can go one axiom, then negate this axiom to something else, then another axiom, negate it. So we just breaking the laws in a certain way by negating them, going to opposite, right? Going to opposite. And actually, this thing was done with geometry. There was a famous guy. His name is David Hilbert. Hilbert. Not Hobbit. Hilbert. Okay, Hilbert, right? He lived in the beginning at the end of 19th century to the beginning of 20th century. Actually, he died somewhere in 40s of 20th century. He was a famous mathematician, actually physicist too, but mostly mathematician. So what he did actually, he took all the list of the axioms of geometry, Euclidean geometry, and he step by step negated one axiom, then the second axiom, the third, I forget the exact number, something like 10 axiom or something, and he created 10 versions of geometries. Each one negating these things. If you think that it is something very, very far from us, it's not actually correct, because like for the first axiom that we're talking, and for this parallel too, if we look at geometry on our Earth, the actual geometry on Earth, right? So we have North Pole, right? There's South Pole, right? And the analogs for the straight lines, so the shortest line on the globe, on our sphere, right? On our planet, spherical, close to spherical, right? So the shortest way is so-called geodesic, right?
What?
Geodesic. It is called geodesic line. It is the shortest line. It's analog to straight line.
Shortest path.
Shortest path, yes. Shortest path, yes. It's analog to straight line, but it's not. It looks straight when you really put a line on Earth, right, with special devices like special geodesical tools. You will see it like straight, but actually it's not straight because the surface is curved. Just the curvature is very, very low, so we can see like for many miles almost straight, right? So what are these lines, which is shortest lines? Like from North Pole to South Pole, those line goes like this. Watch this. You see?
Yeah.
They're called meridians. When the lines from North Pole to South, they're called meridians.
But think about how interesting it is. What is the shortest path from you to Katya?
Okay.
It's straight line, right?
Okay, but take a look. Shortest path, right? But you see, it's pretty obvious that they intersect here and here.
Attention together.
They look very parallel here in a distance like maybe 5 kilometers, right? Like this. They look like parallel, but actually when you go further and further and goes closer and closer and intersects in the North Pole, and you go back, they intersect in the South Pole. And also, if you ask how many lines you can draw through 2 points, so here we 2 points, south and north, how many straight lines in the straight lines like geodesics, the shortest paths, how many of these you can actually draw through these 2 points, north and south? What do you think?
You can't because it's round.
How many?
How many?
0 straight lines.
Oh, are you asking about straight lines?
I'm asking about analog to straight lines. Here's the lines that goes with this geometry of the spheric Earth, right?
Lines.
Geodesics. How many geodesics you can pass through North and South Pole? Huh?
2.
Okay, 2 here. What about this?
Many.
How many?
Did it infinite?
Yep. Exactly. Just okay. There are meridians. If you look at the globe, you see meridians drawn there, right? So infinite, yeah.
That's weird. Think about it.
So in this geometry, it's called spherical geometry. In this geometry, you can pass through 2 points. You can pass infinite number of, so not straight, but lines which are close to straight.
But remember,
The same thing with parallels, right? So
one line through 2 points.
yeah. So this is geometry. Now let's. Now look at the other thing, like arithmetics, right? We have something which we call zero. Zero is a very, very interesting thing. It is called a number, but it's actually not a number. It's
Wait, can I just tell you? Can I tell you?
okay. Tell me.
It just separates the negative and positive numbers.
Oh yeah, right. It's a border. Right, and this is very clever. Yeah, it's a border between negative and positive, and it means, like, for example, it's not exactly a number. It's a number, but very interesting. Zero, we can write it like, for example, 1 minus 1. Can we?
Yeah.
It's still zero, right?
We can. There's infinite ways to make zero.
All right. So, but look, interesting to look at them, right? 1 and minus 1. There's still 1 here, but it's separated from minus 1, but actually it's the same zero. Okay. Like there's maybe 5 minus 5 and whatever, right?
Minus 5.
Can it be infinite minus infinite?
But that's still infinity. David, that's still infinity. No
There-
matter what you do to infinity.
There are infinite, it's called representation, a different representation of zero, right? And can it be represented like infinity minus infinity? Huh?
No, it can't. Infinity minus infinity is still infinity.
Okay, let's have a question on this. You think on this, okay? Can it be represented like 0 minus 0?
Yeah. Yeah. Yes.
You think
Which is
so, right?
weird.
Okay, this is another question, right? Just think about those things. Can it be or can it? Or maybe.
I'm not really sure if we can equal zero.
Okay. By the way, there's interesting example of this representation, 0 minus 0. And remember this, 1 and minus 1, it's a symmetry, right? Opposite symmetry, which actually preserves 1, right? Preserves 1. In physics, right, we have the
I
things.
have a question.
Okay.
Is it the closer to zero you get, the closer to infinity you get?
I think this is confusing with 1 over x. But
What?
The closer you get to zero, do you get closer to infinity?
In a certain way, but we'll talk about this. Okay. Just first tell just small example. Okay. On physics, right? In physics, we have certain things which you heard, of course. It is called matter, right? Just matter.
Oh, matter.
Everything is made of matter, right? And also we have something which is called antimatter.
If everything is made of matter, then there can't be such thing as antimatter.
No, there is antimatter. Physically, it's proven experimentally, and also a pretty interesting thing happens when matter, okay, touches antimatter, right? Matter and antimatter, right? It's called annihilate. Annihilate. They destroy each other in a big explosion, huge explosion. Actually, the most amount of energy can be taken out of matter is when matter meets antimatter. And in physics, it is defined exactly like minus, like plus 1 gram, minus 1 gram of matter. Okay. Actually, antimatter goes back in time.
Oh yeah.
But
what if 1 gram of matter explodes with 1 gram of antimatter. Is that zero?
Exactly, that's interesting thing. Yes, the method. Okay, that's interesting thing. The matter, which we know, right? It disappears, but something is preserved. This one, right, is preserved, and this one is called energy. So matter and antimatter produces energy, which is looks like matter. It is matter in a certain way, but it has a very different features. The energy, like photons or whatever. So something happened, something interesting. We wouldn't go too further, but just for you to know that matter and antimatter somehow annihilate each other and produce something which is preserved, which is called energy. Energy is the same. Remember this this famous formula E mc squared, right? This is energy, this is mass or matter, and C is just a proportional coefficient. So that just small example, just for you to think and to use your fantasy with this. And for your questions about 0 and whatever, right? If you have 1 and divide it by 0, it actually goes to infinity. The same thing, if you have 1 divided by infinity, you come to 0. It's a little questionable writing, but anyway, just that thing good to have in mind. So those, you see, this about this 0, both 0 and infinity, they are at the border. They actually divide. Okay, if you see it like here, like 0, right? Remember this, right? This +1, -1, right? +2, -2, right? Here goes to plus infinity. Here goes to minus infinity. But it's still infinity. And if you go to infinity, go there, you return to this from minus.
We know, because they equal the same thing.
Yeah, so 0 is the border and the infinity is the border too. And they are connected with this way. So this, you may say that 0 and infinity are actually two sides of the border, right? One side is on the left, or this part, and this is not this part, right? Right. Left and right. So these all are borders. Okay, so we have our like 30 minutes, right? And I have certain questions to you. Any questions to this first? Any more questions on this?
No.
No. Okay. What I want you to think of and to answer to your papa, right? Okay. First is like, remember I said, what is 0 to 0? Infinity divided by infinity. Oh, what it is? What is this? Like in a 0 minus 0, infinity minus infinity, right? The first question, understand that. The second is, what is, for example, okay, 2 zeros, so 2 multiplied by 0, right? Minus 0.
0. 0.
Okay. 3, 0 minus 0.
0.
There's 3 zeros, and you minus 1 0.
0.
How many zeros you have?
1 0.
Okay, is 0 something out of this world? What do you think?
No.
We can count anything, right? This is a universal law of the universe, right? We can count whatever we want to. We can count cows, third tree is galaxies, universes. Definitely we can count zeros. So 3 zeros minus 1 zero. How many zeros? Okay, just think about it, okay? This is the question.
The difference between 1 0 and 2 zeros. There isn't.
Okay, now the third question is, okay, there are like 3 zeros divided by 0. What is this?
Oh no, you have 0 divided.
Undefined. You can't divide by 0.
Oh yeah, that's 0 divided by 0.
Infinity divided by 3 infinities.
Look, infinity divided by 3 infinities.
That's the same as infinity divided
Oh, by the
by...
way, here again, like 3 infinities minus infinity. Okay, what is this? So, and also think about what is this 0 squared divided by 0 and
Same thing as 0 divided.
infinity, like maybe third to the power of 3 divided by infinity.
That's also undefined.
Okay, this is too easy, okay? Just
That's
think.
infinity squared.
Yes, I agree that it's in like in standard algebra it is undefined, but standard algebra is a certain of axioms, right, which may be modified, right, and they are modified actually, and they are modified in a certain way, in very powerful way. Modern calculus, it's called calculus. Modern calculus worked with all these things, so you think about it. You got your answers. You talk with Papa, and
No, but the calculus doesn't work with that. Calculus works with limits.
Money.
okay.
1 plus 1 money.
Antosha, you should think too.
Never.
Any questions?
Nope.
Okay, guys. Okay.
Thank you very much.
Thank you. Thank you. See you next time.